So let's talk about root locus. Okay, what is root locus? Well, root locus is a handy way of taking a system, looking at the open loop transfer function, and finding the open loop poles and zeros, and then graphing them and revealing the migration paths and the behavior of the closed loop system. So usually it's a bit more work to find the closed loop system behavior and reveal that. And what you can do is by examining the open loop behavior and finding the poles and zeros that way, you can get all of that graphically. And so what we're going to be doing is taking a system, and let's say we have our standard configuration. Let's say we have a YC coming into our system like that. We'll have a negative feedback, and this will be going into some, let's say, G1, and we'll have this gain K right here. Okay, and this will be of S. Our output of our system will be Y, and we'll send this through another block, G2 of S. So we'll have this right here, kind of a configuration. Now what we want to think about is, what is the open loop? Okay, well, the open loop transfer function, GOL, is going to be K times G1 times G2. I'm actually not closing the loop, I'm not completing the system, and I can't plug this in and have a YC input and a Y output the same way that I do here. The input, output, and this will not replace this system, if that makes sense. Whereas with the closed loop transfer function, it would. And we've already found the closed loop transfer function in a previous example. But what we can do here is envision that instead of all of this, we would have, let's let the G1, G2 be this G of S. And if we want to rewrite this, we can write it something more that kind of envisions or kind of is similar to our standard configuration. So then we could have the YC coming in and go through this KG of S block, have this Y output, and have a feedback like this. Okay, so this is my open loop transfer function right here. Whereas we've been used to finding, again, a closed loop transfer function, which we could then draw in and replace this whole middle section. Okay, so they are different. Okay, so you can envision the open loop transfer function as having a polynomial on top and a polynomial on bottom, as with any transfer function. So GOL is going to be some K. Now I want to keep this K out because this is very important. I'm about to explain why. Polynomial S over another polynomial of S. Okay, and again, with any transfer function, remember we were talking about having zeros be the system roots for the polynomial in the numerator, and poles be the system roots for the polynomial in the denominator. Okay, so that's still true. Okay, all right, but this parameter K is something that we're going to vary. Now normally you think about it as K varying from some K initial to K max. And normally this is going to be from 0 to about like positive infinity or some very large positive number. And you can do it for negative numbers, but what we're going to be looking at is mostly in this range. So we'll have k min greater than or equal to, or I'm sorry, less than or equal to k, which is less than or equal to some k max value. Okay, and usually, again, this is 0 and this is some very large number we envision as a positive infinity. Okay, and what we're going to be doing is solving for the roots of the polynomial on top, getting the zeros, solving for the roots of the polynomial in the denominator, getting the poles, and then graphing them. So what we're going to look at, it's going to be a graph in the complex plane, imaginary and real axes. And when we have a pole, let's say we had a pole at 0 and another pole at positive 10. Okay, so those are going to look like x's. So we plot them like this. If I had, say, a 0 at negative 10 and a 0 at negative 2, that would look like this right here. So I have the negative 2, 0 right there and the negative 10, 0 there. And so we've got some rules that we can go through for sketching. Now, in around 1950, or let's start over, about 1950 or so, a mathematician named Evans came up with several rules for sketching these root locus so you could determine what the graph looked like. It turns out that about 7 of those rules are very useful for this class, very useful for us. And so we'll be going through those rules, explaining them, and what they mean for the graph. There are a few rules that we'll use again and again and again and will be most useful to us. So let's do that. And we'll start first with the definition. Okay, so root locus, if we were to define it, it is the migration path of closed loop roots as the chosen root locus parameter. In this case, it's going to be k, varies. Okay, as we vary that k over that k min to k max range, we're going to see the branches fill out. Okay, and then this is usually 0, k, and then some very large number, which we will say positive infinity here. So the closed loop roots are shown on the graph. And then they are also determined by the open loop poles and zeros. Okay, and we can write that as GOL equal to some k gain, that's our locus parameter, P over Q, whereas these are polynomials. Okay, and if you recall, P is going to be of nth degree, whereas Q is going to be of nth degree. Okay, all right, so let's go through the sketching rules and what a typical sketch would look like. All right, so what we're going to start with is rule number 1, and that is called the starting rule. So in general, you have a pole and the branch as it fills out. So root locus sketches are going to look something like, say, this right here. We'll have this will be the symbol for a pole, this will be the symbol for a zero, and then this will be the branch right here. And this, of course, is the real axis and the imaginary axis. So in general, a pole will migrate towards a zero. What rule number 1 explains is that the branch, the start part right here that I filled in, starts from the pole. So we always start from the pole, and if we migrate somewhere, we migrate towards a zero, but we start here at the pole. Okay, so that's pretty simple. Rule number 2 is the stopping rule, and that's really just the second part of what I said there, that if we're going to stop a branch, this branch right here, we start from the pole and we stop at this zero if we have a zero. If we don't have a zero, then we have a special case where we would reach a virtual zero. So we always go from pole to either real zero or a virtual zero, which is made up of imaginary zeros on the unit circle out here at a radius of infinity. So if this zero right here didn't exist, let me do a second case down here just to illustrate. So I had this right here. And we had a case where the pole was actually reaching a virtual zero. It would go off into a radius of infinity, trying to reach this virtual, I'll say dotted line zero, virtual zero. And that's pretty much the starting and stopping rules right there. Okay, so let's talk about rule number 3. Rule number 3 is a rule that will be used in almost every single graph that we draw, and that is called the real axis rule. Okay, so what the real axis rule explains is that if I'm drawing the root locus, imaginary and real axis right there, if I'm drawing root locus, in order to fill out the branch, what I want to do is plot everything I've got, just make the x's for the poles and the circles or zeros for the zeros. What I want to do, and let's fill this out real quick. I'm gonna put a pole here, and if you've got numbers and you're plotting this, make sure that you label your axes. I'm gonna do an example right here, so I'm gonna put let's say this is at 4, for example, and I'm gonna put a 0 here at -2. So this is what a 0 looks like, this is what a pole looks like. So if we were using the real axis rule, what I would do is I would try to fill in branches on the real axis. And what I want to do is locate something. In this case, I'll just go ahead and locate this pole, and I want to look rightward. Anything that is an odd number, if I'm looking rightward and I have that odd number, then I can fill out a branch. 0 is actually, we say that's even, and so we don't fill in a branch. So if I come here and I look rightward, this is even because there's nothing here. But if I keep going, well, if I'm looking rightward at this point, I can see that I've got one thing right here. So summation of the poles and zeros is what we're looking for. So if I'm looking rightward, like right here, I can see that I've got one pole. So I need to start filling in this branch on the right, the real axis. I can do that all the way up to here where I reach this 0. And then from this point on, I see that I've got an even number of items, of poles plus zeros. So I've got 1 and 2. So I can't fill in any more branches because there's not an odd number. Okay, so that might sound kind of arbitrary, but this is the rule, and we will use this in pretty much every single root locus that we draw. Let me do another example real quick. This is really important to get down. So let's say that I have a double pole right here. I have 2 poles at, let's say, 5. This is the real axis. This is the imaginary axis. And then I'll have a 0 here at 2. And then I'm going to have another 0 out here at -4. Okay, so I want to use the real axis rule to fill in the branches on this root locus. Another note, I'm not necessarily done with a root locus after I use rule number 3. We're only 3 rules in out of 7, so there could be other rules that will apply. Now I know, just from knowing the rules already, that this is actually completed, but say for this one will not be completed just from rule number 3. But let's back up. Let's take it one rule at a time. And for rule number 3, if we were to fill in the real axis branches here, let's do that. Okay, so I'm out here at this point, -10. I'm looking rightward. Let's take this point right here. We're looking rightward. There is nothing. 0 is marked as even. So I have nothing, nothing, and then once I am past the 5 and I'm moving leftward, looking rightward, I have 2 right here. So it's still even. I come out here and I pass this 0. I now have 1, 2, 3. So once I pass the 0 and I'm moving leftward, looking rightward, let's put a marker right here, I can start filling this in. Now I have to keep filling it in until I hit this 0 right here. Once I get past this -4, if I'm looking rightward, then I have an even number, okay? So you're looking for odds, and once you hit even, you have no more branch. So at this point, it's even, it's still even, and then it's odd, and then it's even again. So this is the only area where there's branch, okay? And that's pretty much the real axis rule, okay? All right, so let's keep moving. All right, so we have rule number 4 now. And this is called the collision rule. Okay, so basically the idea behind the collision rule is that if we have let's say 2 poles, okay? So I have a pole here, and let's say that this is at -20, and I have this pole here, let's say it's at -5. And this is the imaginary axis and the real axis. Always got to label those. So let's say that for some reason, actually, you know what? Let's go ahead and use rule number 3, that real axis rule, and fill this out. Okay, so we've got, if I come over here, I have even, and then once I get past this -5, I can start filling this in because looking rightward, I have an odd number of things, odd number of poles plus zeros. So I fill this in all the way until I get to the -20. And then if I'm out here looking rightward, I have 2 items. So I can no longer fill in the branch. Okay, has to be odd, have to have an odd number. So this is all filled in with rule number 3. Okay, so what's actually happening here with a branch? Well, a branch is the symbol of 2 poles moving. So as I vary that parameter k, as I'm increasing it, these poles are moving, and they're actually moving, in this case, towards each other. And we can't have two poles that actually overlap like this. What happens, per the collision rule, is that they move towards each other, and at some point, they collide. Some k value, we'll say k alpha right there, they collide, and when that happens, they ricochet off, or deflect off, that's a better way of saying it, off of the real axis at plus and minus 90 degree points. So plus minus 90 degrees. Okay, and so this pole is moving this way, this pole is moving this way, and then one goes up, one goes down. Now, we'll have more formulas that we discuss about how to find the curvature of this, because they can have a curve to it, about where exactly these are going, and in general, if there are no more poles out here, I mean, if there are no zeros, because we have to have a pole moving towards a zero, they'll go to that virtual zero, that the virtual unit circle kind of radius of infinity zeros. Okay, so they're going off plus or minus degrees, and that's the main idea behind the collision rule. Okay, so let's talk about rule number 5. Okay, this is the collision rule complement. So it's a lot like the collision rule, except what if you don't have real poles? What if you have poles that are complex numbers? So we have imaginary axis here, real axis here, and so you have a pair of poles that are complex conjugates. So if you have one that's complex, you've got to have the other. And so these are, in this case, say, moving towards the real axis. And they are going to collide at some point. And when that happens, at some k alpha collision, they will move off at different angles, deflecting off at 90 degree angles towards, or alongside, rather, the real axis. So they'll go off here. So it's a really similar rule here. We just have to take the complex case into account. Okay, so as we increase that k, this deflection happens, and then they go off in their separate directions. Okay, so the next rule that we'll talk about is rule number 6. And this is called the center of gravity rule. And it's spelled center with the R-E, like this. Okay, so basically, the idea of this is that, remember how we had that GOL that had some K parameter, and I wrote an R there, it should have been a P. P over Q, and the order of this was M, and the order of this was N. So basically, when we have the degrees of P and Q such that we have an N minus M greater than or equal to 2 kind of case, if this happens right here, then the branches will move or migrate so that the sum of these roots, the sum of the closed loop roots are always constant. So we have this sum of closed loop roots remain constant in how the branches move. Okay, so if this is not true for our open loop transfer function, this rule doesn't even apply. So if this is the case, then this rule isn't even useful to us. Okay. All right, and our last rule that we'll talk about is rule number 7. And that is the PoleZero equality rule. Okay, so the basic idea here is if we have an open loop pole and an open loop zero in the same place, that is, if they have the same value. So let's just get our graph out here so that we have an illustration. So if pole 0 have same value, then basically the whole branch just starts and stops here. So this is a fixed point. And that is the entire root locus in that case. So these are the 7 rules that we'll be using the most, and we have a few other formulas